In 2016, astronomers pointed their telescopes at a constellation called Coma Berenices. They found a galaxy, Dragonfly 44. This galaxy was strange. It was huge, about the size of our own Milky Way. But it was almost invisible. The Milky Way has over 100 billion stars. Dragonfly 44 has only about 1 billion. It's a ghost galaxy, a smudge against the blackness of space. The math didn't work. For a galaxy that big to hold itself together, it needed more mass, like a lot more. Calculations showed that 99.99% of Dragonfly 44's mass was something we couldn't see. It was dark matter. This discovery was unsettling. It showed that what we see, the stars and the light, is just a tiny fraction of what's out there. The universe is mostly made of stuff we can't detect. It's a vast, dark, unknown structure. And it forces a question. If so much of our own universe is hidden from us, what else might be out there? What if entire other universes are right next to ours, separated by a gap we don't know how to cross? The search for these other realities isn't just science fiction. It's happening in labs and observatories around the world. Scientists are running experiments. They are looking for cracks in our understanding of reality. They are trying to prove that we are not alone in the cosmos, not just on other planets, but in other worlds entirely. Number 15, the double slit, still baffles everyone. A single particle of light, a photon, can be in multiple places at once. If you fire a single electron at a barrier with two slits in it, it will somehow pass through both slits simultaneously. The first version of this experiment was performed by Thomas Young in 1801, long before anyone knew what an electron was. He did it with light, and it showed that light behaved like a wave. But in the 20th century, things got much stranger. Scientists like Claus Johnson in 1961 finally managed to perform the experiment with individual electrons. They expected the electrons, being particles, to go through one slit or the other like tiny bullets. They expected to see two distinct bands on the detector screen behind the slits. But that's not what they saw. They saw an interference pattern, a series of bright and dark bands. This is the pattern you get when waves interfere with each other like ripples in a pond. A single electron was behaving like a wave. It was interfering with itself. This meant it had to have gone through both slits at the same time. The truly bizarre part came next. The scientists decided to watch. They placed a detector by the slits to see which path each electron actually took. You know, as soon as they did this, the behavior changed, the interference pattern vanished. The electrons started acting like normal particles again, going through one slit or the other. The detector screen now showed just two bands, exactly as you would expect from tiny bullets. The very act of observing the electron forced it to choose a single path. It was as if reality knew it was being watched. This is the core mystery of quantum mechanics. It's called wave-particle duality. Everything at the quantum level can act as either a particle or a wave, depending on whether you are looking at it. But how does this suggest parallel worlds? A physicist named Hugh Everett III came up with an explanation in the 1950s. It was called the many worlds interpretation. Everett said there's no mystery. The electron doesn't choose a path. It takes all possible paths. Every time a quantum event has more than one possible outcome, the universe itself splits. So when the electron reaches the barrier, the universe splits into two. In one universe, the electron goes through the left slit. In another identical universe, it goes through the right slit. We, the observers, only exist in one of these branches, so we only see one outcome. When you don't watch the slits, these different universes, these different paths can interact with each other. The wave from the left slit universe interferes with the wave from the right slit universe, creating the interference pattern. But when you place a detector, you become part of the system. Your own state becomes entangled with the electron. The moment you measure the electron going through the left slit, you have entered the universe where that happened. The other universe, where it went through the right slit, branches off and continues on its own, completely inaccessible to you. The double-slit experiment in this view is a direct window into the multiverse. You know, it's not just a clever trick of probability waves, it's the constant, ongoing creation of new worlds. Every quantum event, from the decay of a radioactive atom to a photon hitting your eye, is splitting reality. This idea was so radical that Everett's work was mostly ignored for decades, but as the weirdness of quantum mechanics has been confirmed again and again, his interpretation has gained more and more followers. The experiment itself, simple in its design, remains the most profound and direct challenge to our idea of a single solid reality. Number 14, erasing the past with quantum choices. A decision you make in the present can seemingly alter an event that has already happened in the past. This isn't a theory, it's the result of a real experiment called the delayed choice quantum eraser. It's an experiment performed in 1999 by a team led by Marlon Scully, took the double-slit experiment to a new level of strangeness. A measurement made on a particle can determine the past behavior of its entangled twin, even after that twin has already finished its journey. Here's how it works, in simple terms. The setup starts like the double-slit experiment, but it's more complicated. Special crystals are used to create pairs of entangled photons. Let's call them photon A and photon B. They are linked. Whatever happens to one instantly affects the other, no matter how far apart they are. Photon A is sent towards the double slits. Photon B is sent on a much longer path to a separate set of detectors. Photon A goes through the slits and hits a detector screen, just like in the original experiment. Its journey is over and done with. It has already made its mark. Meanwhile, photon B is still traveling. The experimenter now has a choice. They can either measure which path information for photon B, or they can erase that information. If they choose to measure which path its twin, photon A, must have taken, they use a certain detector setup. If they want to erase that information, they use a different setup. The key is that this choice is made after photon A has already hit its screen. The results are astonishing. If the experimenter decides to measure the path information for photon B, the pattern created by all the photon A's on their screen shows no interference. The photons acted like particles. They went through one slit or the other, but if the experimenter chooses to erase the path information for photon B, the pattern from the photon A's magically resolves into an interference pattern. The photons retroactively acted like waves. Let that sink in. The choice made about photon B here and now determined whether photon A acted like a particle or a wave back then. It's as if the past is not set in stone. This experiment does not violate causality. You can't use it to send information back in time. The full pattern is only revealed when the data from both photon A and photon B are brought together and compared. An observer looking only at photon A's screen would just see a random-looking scatter of dots. But it shatters our everyday intuition about time and reality. How does this connect to parallel worlds? The many worlds interpretation offers a clean, if mind-bending, explanation. When photon A goes through the slits, the universe splits. There is a left slit history and a right slit history. These two histories coexist as waves. When photon B is measured later, the measurement entangles the observer with one of these histories. If the measurement reveals left slit information, the observer finds themselves in the branch of the multiverse where that history became real. If the information is erased, the observer remains in a superposition of both histories, and the interference between them becomes visible when the data is correlated. There is no spooky backward in time influence. All the potential pasts exist simultaneously in different branches of the multiverse. The delayed choice is not changing the past. It's simply selecting which pre-existing past you end up examining. The experiment acts as a probe, allowing us to see the ghostly outlines of these parallel histories before a final measurement forces us into a single one. It suggests the past, present, and future are not a single line, but a vast branching tree of possibilities. Number 13, listening for the echoes of colliding universes. In 2004, astronomers studying a map of the early universe found something strange. There was a patch of sky that was inexplicably cold. It's known as the CMB Cold Spot. The map was of the cosmic microwave background, or CMB. This is the oldest light in the universe, a faint afterglow from the Big Bang, emitted about 380,000 years after the universe began. It fills all of space, and its temperature is incredibly uniform at about 2.73 Kelvin. But there are tiny fluctuations, hot and cold spots, that represent the seeds of galaxies and cosmic structures. The cold spot is much larger and colder than standard cosmology predicts. It's about 70 microkelvins colder than the average, which might not sound like much, but on a cosmic scale, it's a huge anomaly. The chance of it being a random fluctuation is less than 2%. This has led to some exotic explanations. One of the most fascinating is that the cold spot is a scar. It's a bruise on our universe left over from a collision with another universe long ago. This idea comes from a theory called eternal inflation. The Big Bang might not have been a one-time event. Instead, our universe could be just one bubble in a vast, churning cosmic foam. New bubble universes are constantly inflating and growing, and sometimes these bubbles can collide. If another bubble universe bumped into ours in the very early moments of its existence, it would have left a mark. The collision would have pushed energy out of that region of space, creating a disturbance. As our universe expanded over the next 13.8 billion years, that initial disturbance would have stretched out to an enormous size. We would see it today as a giant cold spot in the CMB. Laura Mersini-Houghton, a physicist at the University of North Carolina, is a leading proponent of this idea. She and her colleagues have made specific predictions about what such a cosmic bruise should look like. They argue that it wouldn't just be a cold disk, but it would have other subtle signatures in the polarization of the light from that region. The search for these signatures is an ongoing experiment. Satellites like WMAP and Planck have mapped the CMB in incredible detail. Scientists are combing through this data, looking for evidence that supports or refutes the collision hypothesis. For a long time, a leading alternative explanation was that the cold spot was simply an illusion caused by a massive supervoid between us and the CMB. A supervoid is a vast region of space with far fewer galaxies than average. Its gravity would affect the light passing through it, making it appear colder. However, recent surveys have mapped that region of space and found that while there is a void, it's not large or empty enough to explain the full temperature drop of the cold spot. This has renewed interest in the multiverse collision idea, so the experiment is observational. The lab is the entire sky. The equipment is our most powerful telescopes and satellites. We are looking back in time to the dawn of our universe, searching for the fossilized evidence of an encounter with a parallel world. If the telltale signs of a collision can be confirmed in the CMB data, it would be the first direct observational evidence that other universes exist. It would change our place in the cosmos from being the one and only stage to being just one island in an infinite archipelago of worlds. Number 12, searching for gravity leaking through the walls. Gravity is weirdly weak. This is a huge puzzle in physics known as the hierarchy problem. Consider the four fundamental forces of nature. The strong nuclear force holds atomic nuclei together. The weak nuclear force governs radioactive decay. The electromagnetic force holds atoms together and creates light. And then there's gravity, which holds planets, stars, and galaxies together. The first three forces are, in their own domains, incredibly strong. But gravity is shockingly feeble. A simple refrigerator magnet can overcome the gravitational pull of the entire Earth to lift a paperclip. Gravity is about a trillion times weaker than the electromagnetic force. Why? One radical explanation comes from string theory and M theory. The idea is that our universe is not all there is. We might be living on a three-dimensional brain, like a sheet of paper floating within a higher dimensional space called the bulk. The particles and forces of the standard model protons, electrons, electromagnetism are stuck to our brain. They can't leave it, but gravity is different. Gravity, in this theory, is a property of space-time itself. It is not confined to our brain and can leak out into the extra dimensions of the bulk. This would explain why gravity is so weak in our experience. It's not actually weak at all. It's just that most of its strength is diluted, spread out across these other dimensions that we cannot perceive. We only feel the small fraction of its force that happens to stick to our brain. This isn't just a philosophical idea, it's a testable hypothesis, and the place to test it is the Large Hadron Collider LHC at CERN. The LHC is the most powerful particle accelerator ever built. It smashes protons together at nearly the speed of light, recreating the conditions of the very early universe. The main goal is to find new particles and understand the fundamental laws of physics. If these extra dimensions exist, the LHC might be able to find evidence for them in two ways. The first is by creating tiny, microscopic black holes. According to standard physics, you'd need immense amounts of energy to create a black hole. But if gravity can leak into extra dimensions, its true strength is much higher at very small distances. This means the energy required to create a miniature black hole could be within the LHC's reach. These tiny black holes wouldn't be dangerous. They would be incredibly hot and evaporate almost instantly, decaying into a spray of ordinary particles that the LHC's giant detectors like Atlas and CMS could see. Finding such an event would be a spectacular confirmation of extra dimensions. The second way is by detecting missing energy. When particles collide at the LHC, physicists carefully track all the debris. Energy and momentum must be conserved. Everything has to add up. But if a new particle is created that can travel into the extra dimensions, it would carry energy and momentum away from our brain. To the detectors, this particle would be invisible. It would just disappear. What they would see is an imbalance. The energy after the collision would be less than the energy before. This missing energy signature could be the calling card of a graviton, the particle of gravity escaping into the bulk. So far, the LHC has not found conclusive evidence of either miniature black holes or missing energy that points to extra dimensions. The experiments are ongoing. Every time they increase the energy and the number of collisions, they are pushing the frontier of what we can see. The search continues for a sign that gravity is not what it seems, and that our world is just one thin slice of a much larger hidden reality. Number 11, the case of the disappearing neutron. A free neutron, when pulled out of an atomic nucleus, is not stable. It will decay into a proton, an electron, and an antineutrino. This process takes, on average, about 14 minutes and 39 seconds. But there's a problem. 4 years, physicists have been trying to measure this lifetime precisely, and 2 different types of experiments give 2 different answers. The discrepancy is small, only about 9 seconds, but it has persisted for years and is outside the bounds of experimental error. This is the neutron lifetime puzzle, and one of the most outlandish explanations is that some of the neutrons are not decaying at all. They are disappearing into a parallel universe. The 2 measurement methods are very different. The first is the bottle method. Scientists trap a known number of ultra-cold neutrons in a magnetic bottle and simply wait. After a certain amount of time, they count how many are left. From this, they can calculate the average lifetime. This method consistently gives a shorter lifetime, around 14 minutes and 39 seconds. The second is the beam method. Scientists fire a beam of neutrons through a particle detector. They don't count the neutrons themselves, but the protons that are created when the neutrons decay. By counting the emerging protons and knowing the intensity of the original beam, they can calculate the neutron lifetime. This method consistently gives a longer lifetime, around 14 minutes and 48 seconds. A 9-second difference might seem tiny, but in precision particle physics, it's a huge gap. It suggests that something is fundamentally wrong with our understanding, or that one or both of the experiments have some hidden error. Or it could be something much more exciting. A theory proposed in the 1990s suggests the existence of a mirror world. This would be a parallel universe made of mirror particles that interact with each other through mirror forces, but which barely interact with our world at all. The only force that might connect our worlds is a modified form of gravity, or perhaps some new very weak force. According to this theory, a neutron in our world could, under certain conditions, transform or oscillate into a mirror neutron. This mirror neutron would then be part of the mirror world and would be completely invisible to our detectors. In the bottle experiment, some of the neutrons wouldn't decay, they would just vanish from the bottle by turning into mirror neutrons. This would make it seem like they decayed faster than they really did, leading to a shorter measured lifetime. In the beam experiment, you only count the protons from the neutrons that do decay in our world. The ones that transform into mirror neutrons are simply not counted, so they don't affect the result. This would explain why the beam method gives a longer and perhaps truer lifetime. This is a testable idea. Scientists at places like the Oak Ridge National Laboratory are running experiments to look for this specific phenomenon. In one experiment, they fire a beam of slow neutrons at a thick, impenetrable wall. A detector is placed on the other side of the wall. Normally, no neutrons should get through, but if a neutron can oscillate into a mirror neutron, it could pass through the wall without interacting with it, because mirror matter doesn't interact with our matter. Then, on the other side, it could oscillate back into a regular neutron and be picked up by the detector. So far, no disappearing and reappearing neutrons have been found, but the experiments are getting more sensitive. They are pushing the limits on how strongly our world can be connected to a mirror one. The humble neutron, a basic building block of our reality, might hold the key. Its puzzling behavior could be the first concrete evidence that we are living alongside a silent, invisible world that is an almost perfect reflection of our own. Number 10, dark matter might be a neighbor's shadow. About 27% of the mass and energy in the universe is made of something called dark matter. We know it exists because we can see its gravitational effects. It's the invisible glue that holds galaxies together. Without it, stars on the outer edges of galaxies would be moving so fast they would fly off into space. We see its effects in the way light from distant galaxies is bent by gravity, a phenomenon called gravitational lensing. But we have never directly detected a single particle of it. For decades, physicists have built incredibly sensitive detectors deep underground to shield them from cosmic rays, waiting for a dark matter particle to bump into one of their atoms. So far, they have found nothing. This has led some to ask, what if dark matter isn't a particle at all? What if it's the gravity from another universe leaking into ours? This idea comes directly from the brain world scenarios we discussed earlier. Imagine our universe is a 3D brain. Now imagine another 3D brain, a parallel universe floating very close to ours in a higher dimensional space. The distance between the brains could be smaller than the diameter of an atom. On this other brain, there could be its own matter, its own stars, galaxies, and maybe even its own life. The particles and forces of that universe would be stuck to its brain, just as ours are stuck to our own. We would never be able to see it or touch it directly, but gravity is different. Gravity is a property of the space between the brains, so the gravity from the matter in that parallel universe could reach across the gap and affect our universe. From our perspective, we would feel this extra gravity, but we wouldn't be able to see the matter that's creating it. We would call it dark matter. In this model, the strange halos of dark matter surrounding galaxies are not halos of exotic, undiscovered particles. They are the gravitational shadows of ordinary galaxies existing on a nearby parallel brane. This theory makes some interesting predictions. If dark matter is the gravity from another world, then it might not behave exactly like particle dark matter. For example, it might not clump together in the same way. The distribution of dark matter in galaxies and galaxy clusters could hold clues. Astronomers are mapping the distribution of dark matter with ever greater precision using gravitational lensing. These maps can be compared to the predictions of different theories. Another possibility is that if the branes are close enough, there might be some very weak, non-gravitational interaction between them. Perhaps a particle could tunnel from one brane to another if it has enough energy. This is highly speculative, but it's not impossible. It could lead to strange signals in particle accelerators or cosmic ray detectors. This idea is appealing because it solves two problems at once. It explains why gravity is so weak, it's diluted across the extra dimensions, and it provides an explanation for dark matter without needing to invent a whole new family of undiscovered particles. The experiment here is indirect. It involves a combination of high-energy physics, precision astronomy, and cosmology. By studying the largest structures in the universe and the smallest interactions of particles, scientists are looking for deviations from the standard picture. They are looking for signs that the invisible mass holding our cosmos together is not a substance within our universe, but the faint, ghostly touch of another one right next door. Number 9 is Spacetime, a Pixelated Hologram. In the 1990s, physicists like Gerard Hooft and Leonard Susskind were wrestling with the physics of black holes. They stumbled upon a deep paradox related to information. According to quantum mechanics, information can never be destroyed. But according to Stephen Hawking's work, black holes evaporate over time, and it seemed like the information about what fell into them would be lost forever. The resolution to this paradox led to a stunning idea, the holographic principle. It suggests that all the information contained within a volume of space, like a room or an entire universe, can be described by a theory that lives on the boundary of that space. In other words, our three-dimensional reality might be a projection, a hologram of information encoded on a two-dimensional surface at the edge of the universe. This sounds like philosophy, but it has real physical implications. If our 3D world is a projection from a 2D surface, then space-time itself might not be smooth and continuous. Just like a digital image on a screen, it might be made of fundamental pixels, incredibly tiny units of information at the smallest possible scale, the Planck length, about 1.6x10 raised to the power of 35 meters. If this is true, then our reality has a limited resolution. There would be a fundamental jitter or noise in the very fabric of spacetime. This led to a remarkable experiment at Fermilab called the holometer. It was designed by physicist Craig Hogan to look for this holographic noise. The experiment was not looking for parallel worlds directly, but for evidence that our universe is structured in a way that is predicted by theories like M-theory, which also predict parallel worlds. Proving the holographic principle would be a major step toward validating the theoretical framework that contains the multiverse. The holometer was a very powerful interferometer. It used two identical L-shaped instruments, each 40 meters long. A powerful laser beam was split and sent down the two arms of each L. The beams bounced off mirrors at the ends and were recombined. Normally, the light waves should recombine perfectly, but if spacetime itself is jittering at the Planck scale, it would cause tiny random fluctuations in the lengths of the arms. This would knock the laser beams slightly out of sync, creating a measurable noise in the recombined beam. The sensitivity required was extraordinary. The holometer had to be able to detect a change in position 1,000 times smaller than a proton. It was one of the most precise measurements of space-time ever attempted. The two interferometers were run in parallel. If a real holographic noise was detected, it should show up in both detectors at the same time because it would be a property of space-time itself. You know, if the noise was just from a passing truck or a local vibration, it would likely only affect one. The experiment began taking data in 2014. After a year of running, the results were announced. The holometer did not find the holographic noise it was looking for. Space-time, at least down to the level the experiment could measure, appeared to be smooth and continuous. But this doesn't mean the holographic principle is wrong. It could be that the noise is smaller than predicted, or that it has a different character. The experiment ruled out one specific model, but the general idea remains a powerful concept in theoretical physics. The holometer was a pioneering attempt to experimentally test the quantum nature of space-time itself. It was a search for the pixels of our reality. While it didn't find them, it pushed the boundaries of measurement and showed how we can begin to ask experimental questions about the fundamental structure of our world, a structure that may be deeply connected to the existence of others. Number 8. When two black holes merge, do they ring a bell in another dimension? On September 14th, 2015, two detectors, one in Louisiana and one in Washington State, felt a tiny vibration. It was a ripple in the fabric of space-time itself, a gravitational wave. The wave had traveled for 1.3 billion years to reach Earth, originating from the violent merger of two massive black holes. This detection, made by the Laser Interferometer Gravitational Wave Observatory LIGO, was a triumph. It confirmed a century-old prediction of Albert Einstein's theory of general relativity and opened a brand new window onto the universe. We can now listen to the cosmos, but these gravitational waves might also carry secrets about more than just our own universe. They could be a probe for extra dimensions. According to general relativity in our familiar 4 dimensions, 3 of space, 1 of time, a black hole merger should produce a specific, predictable signal. There is an initial inspiral phase as the black holes circle each other, a merger phase when they combine, and a ring-down phase as the newly formed larger black hole settles into a stable state. This ring-down is like a bell being struck. The new black hole vibrates, sending out gravitational waves of specific frequencies and damping times. These properties are determined only by the black hole's mass and spin. However, if the brane-world theories are correct and extra dimensions exist, things could be different. In most of these models, gravity is the only force that can travel into the higher dimensional bulk. This means that when two black holes merge, some of the energy might not be radiated as gravitational waves within our brain, but could leak away into the extra dimensions. This would have 2 potential effects on the signal we detect on Earth. First, the amplitude of the waves, their loudness, might be slightly weaker than predicted by standard relativity. We would be missing the energy that escaped into the bulk. Second, the ring-down phase might be altered. The new black hole could vibrate in different ways, exciting Kaluza-Klein modes of the graviton that are associated with the extra dimensions. This would change the frequencies and damping times of the ring-down signal in a subtle but potentially measurable way. So, every time LIGO and its partner Observatory Virgo in Italy detect a black hole merger, they are conducting an experiment. They are testing the predictions of general relativity against the incoming data with incredible precision. They are looking for any tiny deviation, any anomaly that could hint at new physics. So far, every single gravitational wave detection has been perfectly consistent with Einstein's theory. There has been no evidence of energy leaking away or strange ring-down signals. This has allowed scientists to place very strict limits on the size of any large extra dimensions. If they exist, they must be smaller than about 1.6 micrometers. But this is just the beginning. As the detectors become more sensitive, and as new detectors like Kagra in Japan and the future space-based LISA come online, we will be able to see more distant and fainter events. We will be able to measure the ring-down phase with much greater precision. The experiment is to keep listening. The universe is full of these cataclysmic events, black holes and neutron stars colliding. Each one is a chance to ring the bell of space-time and listen carefully to the echo to see if part of the sound is escaping through a door into another dimension. Number 7, changing the laws of physics just a little. One of the deepest mysteries of our universe is why it seems so perfectly tuned for life. There are a handful of fundamental physical constants that determine the basic structure of reality. The speed of light, the strength of gravity, the charge of an electron, and a number called the fine structure constant alpha, which governs the strength of the electromagnetic force. If any of these constants were even slightly different, the universe would be unrecognizably different, and almost certainly lifeless. If the strong nuclear force were a bit weaker, protons couldn't stick together, and atoms heavier than hydrogen would not exist. If the fine structure constant were different by just 4%, stars wouldn't be able to produce carbon and oxygen. The universe appears to be balanced on a knife's edge? Why is this? The multiverse offers a straightforward, if unsettling, answer called the anthropic principle. If there is a huge number, perhaps an infinite number of other universes, and in each of them the physical constants take on random values, then it's no surprise that we find ourselves living in one of the very rare universes where the constants are just right for us to exist. We won the cosmic lottery. In all the other universes where the laws are different, there is no one around to observe them. This is a powerful philosophical argument, but is it science? Can it be tested? The answer is yes, in a way. The experiment is to look for evidence that the constants are not constant at all. If our universe is just one patch of a larger multiverse, perhaps the constants are not the same everywhere, or perhaps they have changed over time. Astronomers can test this by looking at very distant objects. When we look at a quasar that is 10 billion light years away, we are seeing light that has been traveling for 10 billion years. We are looking 10 billion years into the past. This light carries a fingerprint of the atoms it passed through on its journey. When light from the quasar passes through intergalactic gas clouds, certain frequencies are absorbed by the atoms in the cloud, creating dark lines in the spectrum of the light. The pattern of these absorption lines is determined by the value of the fine structure constant, alpha. By analyzing these patterns, astronomers can measure what the value of alpha was in that distant gas cloud billions of years ago. A team of astronomers led by John Webb did just this in the late 1990s and early 2000s. They analyzed light from dozens of quasars and found something shocking. Their results suggested that in the distant past, alpha was slightly smaller than it is today. The change was tiny, about 1 part in 100,000, but it was statistically significant. Even more strangely, later observations from a different telescope, the Very Large Telescope in Chile, seemed to show the opposite. Looking in a different direction in the sky, they found evidence that alpha was slightly larger in the past. This led to the radical idea that the fine structure constant might not be constant across space. It could be that our universe has a dipole structure, with the laws of physics being slightly different in one direction than another. These results are highly controversial. Other teams have analyzed similar data and have found no change in the constant at all. It is incredibly difficult work, and there could be subtle, undiscovered errors in the measurements. But the possibility remains. The experiment continues with better telescopes and better spectrographs. Astronomers are trying to get more precise measurements from more quasars. They are trying to confirm or refute these tantalizing hints. If it were ever proven that a fundamental constant of nature changes in time or space, it would shatter our standard picture of cosmology. It would provide powerful circumstantial evidence that our laws of physics are not absolute, but are merely the local bylaws of our particular corner of the multiverse. Number 6, the fifth force hiding between dimensions. We know of 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. For decades, this has been the complete picture, but some theories that predict parallel universes also predict the existence of a fifth force of nature. This force would be hidden from us, operating only at very small distances. Finding it would change everything. The idea again comes from the concept of extra dimensions. As we've seen, one way to explain why gravity is so weak is to say that it leaks into large extra dimensions. But there's another possibility. The extra dimensions might not be large. They could be tiny, curled up on themselves at a scale smaller than an atom. This is an old idea, first proposed by Kaluza and Klein in the 1920s. In this scenario, all the forces might be unified at a fundamental level, but gravity appears weak to us because it's the only one that can. Feel the shape of these tiny extra dimensions. This could have a measurable consequence. While gravity normally follows a simple inverse square law if you double the distance, the force is 4 times weaker. The presence of these compact extra dimensions would modify the law at very short distances. The force of gravity at the sub-millimeter scale might become much stronger than predicted by Newton or Einstein. This deviation would appear to us as a new short-range fifth force. This is a testable prediction. The challenge is that gravity is incredibly weak to begin with, and measuring it at very short distances is extremely difficult. At these scales, the tiny electromagnetic forces between the test masses can easily swamp the gravitational force you are trying to measure. Despite the difficulty, physicists at several universities, most notably the University of Washington's E.O. Wash Group, have been conducting these experiments for years. They use a device called a torsion balance. It's a modern, incredibly sensitive version of the apparatus used by Henry Cavendish in 1798 to weigh the Earth. The basic setup involves a small pendulum, or bob, suspended from a thin fiber. This bob is placed near another mass. The tiny gravitational attraction between the masses causes the fiber to twist by a minuscule amount. By measuring this twist, the force can be calculated. To search for a fifth force, the experiment is designed to look for deviations from the expected gravitational pull at distances from a few micrometers up to a millimeter. The researchers use carefully designed test masses with holes and slots in them. As the masses are rotated relative to each other, they modulate the gravitational signal at a specific frequency. A fifth force with a short range would produce a different kind of signal. The experiments are a masterclass in precision and the elimination of noise. They have to account for magnetic fields, temperature variations, and even the gravitational pull of the person in the room. So far, these experiments have found no evidence for a fifth force or any deviation from standard gravity down to a scale of about 50 micrometers. This has placed tight constraints on many theories involving extra dimensions. It doesn't mean the theories are wrong, but it does mean that if these tiny extra dimensions exist, they must be curled up even smaller than that. The search is not over. New experiments are being designed to push the boundary down to even smaller scales. The torsion balance is a simple-looking device, but it's a powerful tool. It's probing the darkness right under our noses, looking for a crack in the laws of gravity, a crack that could open up to reveal the hidden geometry of extra dimensions. Number 5, the experiment of pure mathematics. Not all experiments involve hardware, lasers, and particle detectors. Some of the most profound experiments in the history of science have been thought experiments, conducted entirely within the human mind using the tools of logic and mathematics. An M theory is perhaps the grandest such experiment ever conceived. It is an attempt to complete Einstein's dream of a theory of everything, a single, consistent mathematical framework that can describe all the forces and particles of nature. And one of its most startling results is that the multiverse is a mathematical necessity. The story begins with string theory in the 1970s and 80s. The problem was that general relativity, our theory of gravity, and the large-scale universe is incompatible with quantum mechanics, our theory of the small-scale universe. String theory tried to solve this by proposing that the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional vibrating strings. Different vibrations of these strings give rise to all the different particles we see, like electrons, photons, and quarks. It was a beautiful idea, but it had problems. For the math to work, it required the existence of 10 dimensions, 9 of space, and 1 of time. And worse, by the early 1990s, there were 5 different competing versions of string theory. It didn't look like a theory of everything, but a theory of 5 things. Then, in 1995, a physicist named Edward Witten set off a revolution. At a conference, he presented evidence that these 5 different string theories were not competing theories at all. They were just 5 different ways of looking at a single, deeper, underlying theory that existed in 11 dimensions. He called this overarching framework M-theory. The M is sometimes said to stand for membrane, mother, mystery, or magic. The M-theory is not just about strings, it includes higher dimensional objects called brains from membranes. Our entire universe could be a 3-dimensional brain existing within an 11-dimensional bulk. This is the theoretical basis for many of the ideas we've already discussed, like gravity leaking into other dimensions. But the most profound outcome of the M-theory experiment was the discovery of the landscape. The equations of the theory don't produce a single, unique universe. Instead, they have a colossal number of possible solutions. The current estimate is around 10 raised to the power of 500. Each solution corresponds to a different possible universe, with its own set of dimensions, its own set of particles, and its own set of physical constants. This is the string theory landscape. It's a mathematical prediction of a vast multiverse. Our universe, with its specific laws and constants, is just one stable valley in this immense landscape of possibilities. This provides a natural explanation for the fine-tuning problem. With 10 raised to the power of 500 universes to choose from, it's virtually certain that some of them will have the right conditions for life to emerge. M-theory is not yet a complete theory. Its central equations are not fully known, and it has not yet made a unique testable prediction that would allow it to be definitively proven or falsified. This is a major criticism, but it remains the most promising candidate we have for a theory of everything. The experiment of M-theory, then, is the ongoing effort by theoretical physicists to explore this mathematical structure. They are using the most advanced mathematics to try to understand its properties and derive its consequences. Every physical experiment we've talked about at the LHC, with the CMB, with gravitational waves after that, is, in a sense, a search for physical evidence that would confirm the strange, multi-dimensional world that has so far only been seen in the equations of this grand mathematical experiment. Number 4, are we living in a simulation? In 2003, the philosopher Nick Bostrom published a paper that posed a startling argument. He argued that at least one of the following 3 propositions must be true. 1, civilizations almost always go extinct before they develop the technology to create realistic simulations of reality. 2, advanced civilizations have no interest in running such simulations. Or 3, we are almost certainly living in a computer simulation. This is the simulation argument. It's a type of parallel world hypothesis where our reality is not a base reality, but a created one, running on a computer in a higher level of existence. The logic is based on probability. If a civilization can create simulations, it will likely create many of them. Think of all the video games we create. If you assume that simulated consciousness is possible, then for every one real universe, there would eventually be billions of simulated universes. If that's the case, the odds of any given conscious being, like you, being in the one base reality are astronomically small. It's far more likely you are in one of the simulations. This sounds like pure speculation, but some physicists have proposed ways we might be able to experimentally test it. The experiment is to look for the fingerprints of the computer program that is running our world. One idea is to look for the resolution of the universe. Any simulation would have a finite amount of processing power. This implies that reality cannot be infinitely detailed. Just like the pixels on a screen, space-time itself might have a fundamental grid or lattice structure at the smallest possible scale. The Fermilab holometer was one search for this kind of pixelation, although it didn't find it. Another approach proposed by physicist Silas Bean and his colleagues is to look for anomalies in high-energy cosmic rays. Cosmic rays are particles that hit the Earth's atmosphere from space, some with enormous energies far higher than we can create in the LHC. If our universe is a simulation running on a lattice, there would be a maximum possible energy that a particle can have, which is determined by the spacing of the lattice. The physicists calculated that this would create a specific cutoff in the spectrum of cosmic rays. We do observe a cutoff, but so far it seems consistent with natural physical processes. However, a more detailed analysis of the cosmic ray spectrum could reveal patterns that are hard to explain with standard physics, but would be a natural consequence of a simulated reality. A third line of inquiry is to look for glitches, or signs that the laws of physics are not as smooth and perfect as they seem. Perhaps the program running our world has bugs, or maybe the programmers take shortcuts. For example, some physicists have suggested that the processes of quantum measurement, where a fuzzy wave of possibilities collapses into a definite reality, seems like a rendering optimization. The system doesn't bother to calculate the definite state of a particle until a conscious observer needs to look at it. These are long shots. The nature of a perfect simulation would be that it is indistinguishable from reality. The programmers of our universe, if they exist, would likely be smart enough to hide the seams. But the possibility is tantalizing. The experiment is to push our observations to the absolute extremes, to the smallest scales, the highest energies, the most precise measurements. If we find a boundary, a hard limit, a place where the laws of physics seem to break down or show an underlying computational structure, it might be the first clue that our world is not the base reality, but just one of many programs running on a cosmic hard drive. Number 3, the quantum computer's ultimate task. A classical computer works with bits, which can be either a 0 or a 1. A quantum computer works with qubits. A qubit can be a 0, a 1, or both at the same time. This property, called superposition, allows quantum computers to perform a massive number of calculations simultaneously. A computer with just 300 entangled qubits could, in principle, explore more possible states than there are atoms in the known universe. This immense power could solve problems in medicine, materials science, and cryptography that are completely impossible for any classical computer, even one the size of the solar system. But where does this incredible computational power come from? David Deutsch, a physicist at Oxford University and a pioneer of quantum computing, has a radical answer. He argues that the very existence of a working quantum computer would be proof of the multiverse. His argument is simple and powerful. Consider a quantum computer program to find the prime factors of a very large number. A classical computer would have to try the possible combinations one by one, which would take billions of years. A quantum computer, using an algorithm like Shor's algorithm, can solve it much faster. To do this, it has to perform a huge number of intermediate calculations. Deutsch asks, where are those calculations being performed? The computer in our lab is a physical object with a finite number of atoms. It doesn't seem to have the resources to perform a near infinite number of computations. Deutsch's answer is that it's not. The computation is being performed in parallel across a vast number of parallel universes. The quantum computer is a machine that is able to harness the resources of these other worlds. The qubits in our universe are interacting with their counterparts in other universes. The final answer we read out is the result of this massive multiverse-wide collaboration. From this perspective, the experiment is the global effort to build a large-scale, fault-tolerant quantum computer, where companies like Google, IBM, and many university labs are in a race to build machines with more and more stable qubits. In 2019, Google claimed to have achieved quantum supremacy with its Sycamore processor, performing a specific calculation in 200 seconds that they estimated would take the world's most powerful supercomputer 10,000 years. This claim is debated, but it marks a major milestone. If Deutsch is right, then with every successful quantum computation, we are performing an experiment that taps into the multiverse. We are not just manipulating particles in a lab, we are orchestrating a computation across different realities. The proof would not be a single signal or a new particle. The proof would be the machine itself working as predicted. If a quantum computer can solve a problem that is demonstrably intractable for any classical device existing within our single universe, it forces a profound question about the origin of that power. The many worlds interpretation provides a natural, if stunning, answer. It says the power comes from the parallel computation happening in the countless other worlds that branch off at every quantum step. The quantum computer, in this view, is the first piece of technology we have ever built that allows us to directly make use of the existence of parallel universes. It would be the ultimate proof, not because we see another world, but because we have used it to do our math. Number 2, the loneliest particle in the universe. Imagine you have two particles created together in such a way that their properties are linked. For example, they have opposite spin. If one is spin up, the other must be spin down. According to quantum mechanics, until you measure them, each particle is in an indefinite state of being both spin up and spin down at the same time. This linked state is called quantum entanglement. Albert Einstein famously called it spooky action at a distance. Here's the spooky part. You can separate these two particles by a huge distance, across a room, across a continent, or even across the galaxy. The moment you measure the spin of the first particle and find it to be, say, spin up, you instantly know that the other particle, no matter how far away, is spin down. The information seems to travel faster than the speed of light, which should be impossible according to Einstein's theory of relativity. For decades, physicists debated whether this was real or if there were hidden variables. Perhaps the particles were like a pair of gloves separated into two boxes. The first person to open their box and see a left-handed glove instantly knows the other box contains a right-handed one. The information wasn't sent, it was predetermined from the start. In the 1960s, a physicist named John Bell devised a mathematical theorem now known as Bell's theorem that could experimentally distinguish between quantum mechanics and these hidden variable theories. A series of experiments, most famously by Alain Aspect in 1982, and by many others since with increasing precision, have confirmed the predictions of quantum mechanics and ruled out local hidden variables. The spooky action is real, but how does it work? The many worlds interpretation offers an explanation that avoids any faster than light communication. It claims nothing is ever sent between the particles. Here's how. When the entangled pair is created, the universe splits. The entire multiverse now contains all possible combinations. When the first observer, let's call her Alice, measures her particle, she doesn't cause the other particle to change. Instead, she becomes entangled with the particle. The universe splits again based on her measurement. In one branch of the universe, Alice measures spin up. In another branch, a different version of Alice measures spin down. Now consider the second observer, Bob, who is light years away. When he measures his particle, he also splits the universe. In one branch, he measures spin up, and in another, he measures spin down. The key is that the correlations were established from the beginning across all the branches. The universe where Alice measures spin up is also the universe where Bob measures spin down. The universe where Alice measures spin down is the one where Bob measures spin up. There is no signal sent between them. They simply, upon measurement, find themselves in a consistent branch of the universal wave function. The spookiness is an illusion created by our limited perspective of living in only one of these branches. Every experiment that tests Bell's theorem is, from this viewpoint, an experiment that probes the structure of the multiverse. These experiments, using entangled photons sent over fiber optic cables or even beamed to satellites in orbit, are confirming again and again the deep and strange correlations that hold our reality together. They don't prove many worlds, but they show a reality that is deeply non-local and strange. The many worlds interpretation is one of the few that takes these results at face value, without adding new rules or spooky actions. It suggests that entanglement is not a mysterious link between two distant particles. It's a connection that exists across the vast branching structure of parallel realities. Number 1, the first question that broke physics. The ultimate experiment that is trying to prove the existence of parallel worlds is not a physical device. It's the intellectual struggle to answer a single question: what happens when we make a measurement? This is called the measurement problem, and it is the foundational crisis of quantum mechanics. It is the question that first led Hugh Everett III to propose his many worlds interpretation in his PhD thesis in 1957. Here is the problem. The central equation of quantum mechanics, the Schrödinger equation, describes how the quantum state of a system evolves over time. It describes a smooth, continuous, wave-like evolution. According to this equation, a particle like an electron can exist in a superposition of many states at once. The equation works perfectly for predicting the behavior of unobserved quantum systems. But the moment we observe the system, something completely different happens. The wave of possibilities seems to collapse into a single, definite outcome. The electron is found here, not there. The radioactive atom has either decayed or it has not. This collapse is not described by the smooth Schrödinger equation. It is a violent, instantaneous, and random jump. Physics seems to have two sets of rules, one for when we are not looking, the Schrödinger equation, and another for when we are the collapse of the wave function. This is deeply unsatisfying. What counts as a measurement? Does it have to be a conscious observer, a camera, a Geiger counter? At what point does the quantum world stop and the classical world begin? This was the basis of the famous Schrödinger's cat paradox, the standard explanation known as the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg, essentially said not to worry about it. The math works for making predictions, and that's all that matters. They accepted the dual rules as a fundamental feature of reality. Hugh Everett found this unacceptable. He asked a simple question: what if there is only one rule? What if the Schrödinger equation applies to everything all the time, including observers and their measuring devices? He took the math of quantum mechanics and followed it to its logical conclusion. His conclusion was radical. If the Schrödinger equation is always true, then the wave function never collapses. When a measuring device interacts with a quantum system in a superposition, the measuring device itself is pulled into the superposition. If an atom is in a superposition of decayed and not decayed, the Geiger counter that measures it enters a superposition of clicked and not clicked. And the scientist who looks at the Geiger counter enters a superposition of saw it click and saw it not click. From the perspective of the scientist, the world appears to split into two distinct branches. In one branch, the atom decayed, the counter clicked, and the scientist saw it click. In the other branch, the atom did not decay, the counter did not click, and the scientist saw it not click. Both outcomes happen, but in separate, non-communicating realities. This is the many worlds interpretation. It is not an addition to quantum mechanics. It is a simplification. It removes the arbitrary and ill-defined rule-of-wave function collapse. It just takes the core mathematics at face value. The experiment, then, is the ongoing debate and research at the heart of fundamental physics. It is the search for any evidence that would favor one interpretation over another. All the other 14 experiments on this list are part of this larger one. A confirmed signal of a multiverse collision in the CMB, the discovery of extra dimensions at the LHC, or the successful operation of a Deutsch-style quantum computer would all be powerful evidence in favor of Everett's vision. His idea was initially met with ridicule. His supervisor, John Wheeler, was hesitant. The great Niels Bohr was completely dismissive. Everett left physics and went to work in military operations research. But his idea never went away. As the decades passed and the weirdness of quantum mechanics was confirmed with ever greater precision, physicists like Bryce DeWitt championed his work and brought it into the mainstream. Today, the many worlds interpretation is one of the leading explanations for what quantum mechanics is telling us about reality. The debate is far from over, but the experiment that Everett started with his simple, powerful question continues. It is the quest to understand the true nature of our universe, even if the answer is that our universe is just one of an infinite number of parallel worlds, constantly branching, constantly exploring every possibility forever.